Hi everyone, this is Ms. Baracco, and today's note taking is going to be on Chapter 5, Section 6. And our topic is going to be exponential growth. And we're going to look at some real world examples of exponential growth using those exponential expressions that we've been practicing to simplify for the past week or so. So the first example we're going to look at says the inventor of the game of chess went to India and he shared his game with their emperor. And basically the emperor said, wow, this game is so cool. I've never done this before. And as a reward for coming up with this very, intellectual activity, what would you like as your reward? So he says, name your reward. And the inventor, he says, for the first box on his chessboard, he wants 1 grain of rice. On the second box, he wants 2 grains of rice. On the third box, he wants 4 grains of rice. On the fifth box, he wants 8. On the sixth box, he wants 16, and so on and so forth. So he describes what he would like as his reward, and basically what we can see as an exponential expression. So for each box, 1, 2, 3, 4, 5, and there are many, many boxes on a chessboard, he wants to duplicate that grain of rice. So again, in the first box, he wants 2 grains of rice, in the second box 4, third box 8, 16, 32, 64, 128. You see what's going on. And in exponential form, we can write the total number of the grains of rice in this fashion. And the question we want to think about is, what pattern do we see? So to get from each step, the rice grains double, or they're multiplied by a factor of 2. And that's very similar to thinking about 2 as a base, given a particular power. So let's think, if a chessboard had 64 squares, how many grains of rice will be on that particular square, the 64th square? And I would, of course, figure that out by doing 2 to the 64th power. Right? When we think about, can we write it as a power? Yeah, absolutely, we can. So let's make a graph. Let's think about what this data looks like. What does an exponential expression look like when we graph it? So on the bottom, I'm going to put like the number of squares. And along the y-axis, I'm going to put the grains of rice. Now, because I'm counting my grains of rice in terms of powers of 2, I'm going to set my scale as 16, just to make it a little easier to see the growth. I want that to be a power of 2. And I'm going to graph some points. I'm going to think a little bit about at 0 squares, what that means, at 1 square, 2 squares, 3 squares, 4 squares. And initially, my data almost looks linear as it slowly starts to increase in its growth and form that exponential curve. So this is kind of interesting. Does it make sense to connect the points on an exponential expression? Now, sometimes it does and sometimes it doesn't. In this particular case, we would say no. And that's because the graph is a discrete graph. What that means is the number of squares that I have is a unique value, and it has to be a whole number value. I can't say that I have 2.5 squares on a chessboard. It's not really something I would measure. So because there are unique data points. We don't connect those data points. I can't tell you at any point along that line how many grains of rice I will have because the grains of rice changes based on the number of squares. The number of squares has to be a whole number. But we can write this data as an equation where s equals the number of squares. So the function of s, the function of squares, is f of x is equal to a base of 2 with an exponent of s, right? Based on the number of squares, 2 to the number of square will give me how many grains of rice will be on that particular square. Great, and that is correct. So this is something we're going to think about. Where in the real world are we going to see exponential expressions?